Hello everybody, my name Akram Hadid. Delegated to present Haider Ardain's slide as he gets his visa delayed. So the name of the paper is MIMS based power delivery control for BERST application. I've divided my presentation into introduction, and here I will let you know why we would think MEMS can achieve more energy saving in a specific kind of application, such as like biomedical device, battery operated device, and wireless sensor network, baseband processor application that's work uh, um, in either uh, uh, medium frequency of operation. And then I would move into motivations modeling, and here I will discuss and describe how we simulate the both technology together in cadence. And then I will move into proposed architecture, result, conclusion, and future work, and I will end up with the references. So introduction: during the last 4 decades, scaling of CMOS transistor has arrived to a point at which any further reduction in threshold voltage comes at the expense of power consumption. As you can see here in this graph, as the gate length drop down, the passive power density approach the active power density, and this energy consumption is too high for portable devices or battery operated devices, baseband processor, biomedical implants, and wireless sensor network. So leakage power approach the active power, and as you can see here in this and the second graph, as the operating voltage scale down, then the dynamic energy goes down. However, the leakage power increase exponentially. The second reason, actually, that the CMOS transistor has been proven not functioning well at high temperature and radiation environments, unlike MEMS relay, which has been proven that doesn't affect by the harsh environment. Uh, in this research, we propose a computing system like a biological system as an example of energy efficient portable gadget architecture. Such a system typically have two types of operation, regular and bursty. So regular activities take place all the time and meant to serve the needs of the overall system, while bursty activities triggered by or in accordance with the needs to react to the demands of the environment. So how we could manage to organize their operation in an energy efficient and robust way? Why not build a computer system in a similar fashion? Constantly active part has to be relatively slow. Fast processing part has to be done in a specialized unit. As you can see here in this graph, uh, this is proposed portable system architecture, which is being published in a sync conference. So a battery operated system, like a biological system, spends a non-trivial proportion of time in standby mode and then shift into regular or burst active mode. As a result, leakage current can drastically lower battery lifetime. To that end, this paper proposed a new paradigm to drastically reduce leakage current in idle period while utilizing the dynamic voltage scaling in bursty regular active mode. So the most of the talk, we're gonna focus on bursty operation and MEMS relay. So, so here in this slide, I would show you how we uh, model and simulate the MEMS with CMOS technology. So, in the paper published in our paper published in one, we used Verilog AMS, uh, uh, Verilog AMS to describe the behavior of MEMS relay by build a switch mode simulator by lumping the electrical and mechanical parameters, and these parameters based on fabricating result in published work. But however, in this paper, we use the COMSOL multiphysics to simulate the MEMS relay. So having the device dimension geometry material, for example, this is the latest MEMS relay, which is called the 4-terminal relay. So having the dimension geometry material and then performing the parametric sweep, so analysis and transit analysis. So a parametric sweep analysis to change all the parameters and see how it goes with the energy and the mechanical delay time and many mechanical time. So and then transit analysis and frequency analysis. So after performing this analysis, we managed to calculate the stiffness of the beam of the MEMS, damping mass, pull-in voltage, the voltage required to make the MEMS relay pull-in, and mechanical time, switching energy. This is from the MEMS side. From the other side, we use visual code to build the to simulate ARM M0 processor, microprocessor, file filter, and this is actually in the future work, but in our work we focus on function block like DSP, RF, and then we use synopsis to simulate and optimize the dynamic and static energy and area as well, and then co-simulate the both technology together in cadence simulator to calculate the total energy and time. So here in this table I will show you some of the parameters that we get from console. So we have MEMS area micrometer, so we change the area from 450 to 100, then the voltage changed from 6 to 15 voltage. As you can see, the mechanical time from 1 to 20, while if we scale down to 2 micrometers square, then you could see the operating voltage ranged between 0.7 to 2.2, while the mechanical delay time from 0.01 to 0.02. The in this time I'm going to talk about the proposed architecture of the power delivery network. So in the first paradigm, they use the variable voltage regulator model has been used. So the shortcoming of this one is that the number of the voltage regulator equal to the number of function block, and this results in the increase the cost higher than the one of fixed output voltage regulator. The power conversion efficiency of multiple V output voltage regulator varies as a function of those V out. So in the second paradigm, which is based on phi, the CMOS layer has been proposed, and this layer is responsible to assign the voltage level to the corresponding function block. So this paradigm has shortcoming regarding to support the low throughput and bursty operation application, because leakage current of CMOS transistor in the power switch network, and especially the number of the leaky paths between the power transistor and function block is increased to supply the required current. In our proposed paradigm, we propose using MEMS relay layer here instead of using the CMOS layer to support the low and medium frequency portable battery operated computing, such as baseband processor, biomedical implants. Increasing leakage power in these devices due to a low duty cycle can lead to difficulties in replacing the battery, and as well the bursty operated devices. So the proposed architecture of power delivery network consists of power switch network architecture. So in this case we use the MEMS. So performs this layer responsible to performs the function of switching the supply voltage level of the function block when a new power performance state is commanded by the power manager. So we use cadence simulator to optimize the width of the power transistor and the number of parallel CMOS transistors required to deliver the voltage, the required voltage. While in MEMS we use multi physics data in table 1 and have been utilized to determine the number and of parallel switch of the mem relay to power gate. So as you can see here, in figure B, in MEMS relay, we need to have a charge pump because the operating voltage of MEMS is very high, ranged between 6 to 15, depends on the dimensions of the MEMS. So as you can see here, uh, uh, that's IOF is 0 in this case because the air separates the drain and source, while here the IOF is about 2.2 microampere, while the number of CMOS transistor in parallel required 44, while here 166 to deliver the same power to the DSP1. The second component of the proposed power delivery net architecture is the power switch controller. So the power switch controller, it's assumed that the transition of the system into different power performance state can be described as a time homogeneous macro of chain. In each state, the supply voltage level of function block is specified as shown in the test bench of figure 4. So, um, so in our study, a power switch controller based on macro of chain has been utilized to switch the power performance state of different function block for 100 cycles. So as you can see here in figure 4, test bench of operating state and state transition, and this is based on paper 9. um, so uh, so transition from state to another state is governed by probability, as you can see here. So in state number 1, as you can see, so DSP1 has to be connected to 0.3 here, to 0.3, DSP2 has become 0.3, while memory 1.3, and the input output 1.3, while RF 1.5. So in our analysis, we measure the energy of the ratio of the energy of MOSFET to the energy of relay for various TOM per cycle. For design power gate by a 90 nanometer PMOS transistor and other power gated by the MEMS relay. So as you can see from the result here, for short TOF, for instance in DSP2 here, so TOF, if the TOF less or equal to 10 microsecond, the increased switching energy of the relay uh, based power gate and or state change overweight its leakage power reduction benefit. So as you can see here, at less than 2 micrometer, the MOSFET can achieve more energy saving than MEMS relay. However, for large TOF, for example 1 microsecond TOF can achieve more energy saving than CMOS transistor based power gating. So even with the current existing MEMS relay, if TON 1000 nanosecond, the curve with red line, and the TOF 10 microsecond, the relay's negligible leakage constantly reduce the total energy as the TOF is increased. So as you can see here, so even though with TON 10 nano 1000 nanosecond, the MEMS can achieve more energy saving if it works after the this point and onward. So then by using COMS or multiphysics, we scale down the MEMS relay into 2 micrometer square, and as you can see from figure 6, scaling of MEMS relay in order to reduce their pass capacitance and switch energy enables to begin accruing relatively high energy saving at substantial lower TOF of 10 to minus 8, about 100 improvement. Result in figure 6 clearly shown that power gating based MEMS relay is always energy efficient regardless of target throughput. So in conclusion, this work proposed an efficient power delivery network for power battery operated devices which can drastically reduce leakage current in idle period while utilizing the dynamic voltage scaling in the bursty or regular active mode. This paradigm is essential for devices with mixed duty cycling, where some parts are required to work regularly and with low throughput, while other parts are activated simultaneously. So results have shown that the proposed board EV network can achieve more than 1000 saving in energy compared to CMOS counterpart for low duty cycle. Here's the last slide, which is some of the referencing, and if you have any question, could you please refer to my email.